So we've been introduced to equations with one variable and practiced manipulating those equations or solving those equations. We've seen how if we have two variables and the x and the y coordinate plane, we could find locations of things on that xy coordinate plane, and that would be ordered pairs, right, where it's always an x and a y. And we're going to roll these ideas together, moving from one variable equations into two variable equations. So these are going to be equations that have both an x and a y in them. We're going to start out in this course with linear two variable equations. And linear, what we're talking about is no exponents yet. So no exponents on any of our variables. And so we're going to have two variables in a linear equation. And basically a linear equation can literally make a line, whoops, on a graph. Now, we're about to come into the videos of me drawing really terrible lines. I try to use a ruler, but I can't with my little tablet thing here. So imagine this is a very straight line, and this could be the line x plus y equals 1. So that's a pretty abstract concept to say that we're going to go from doing math with just numbers to doing math with letters and numbers to now drawing pictures of equations. And so what we're talking about here is that this as a linear equation actually does make a line on a graph that goes on forever in both directions. And so because it goes on forever in both directions, there's actually an infinite number of ordered pairs that we could plug in and have it satisfy that equation. We could verify it with an infinite number of ordered pairs. So here we could have 1, 0 could be a solution to this equation, or we could have 0, 1, right, with this dot right here. And so coming up with an example, figure out where we're going, hopefully make some more sense of these words. So linear equations means no exponents, two variables on them. The solutions to these two variable linear equations are ordered pairs. There's always an x and a y in our ordered pair, always written in that order. There's an unlimited or infinite number of solutions because these lines go on forever. It's not to say that every ordered pair is a solution to these, but you could come up with an infinite number of ordered pairs that would make this equation happy. So here's an example, a standard form of a linear equation. So the solution to a linear equation makes it true, and an ordered pair is a solution. So we're going to start out, before we draw pictures here, in this B2 section is just dealing with these linear equations in a numerical sense. We'll come to drawing pictures more in the coming sections, but let's start out with verifying. So much as we started out with verifying solutions to one variable equations, we're now going to verify solutions to two variable equations. And we do this much the same. And so what we're going to do is take this equation here and we're going to check, is this x and this y a possible solution to this equation? And to do this, we verify it. So left side and right side. What I'm going to do is similar to what I did before, but this time I have both an x and a y to sub in. So copying the left side of the equation, I have a 2 times x, which is a 2, plus y, which is a 5. I've subbed in with brackets. The right-hand side is just a 9. So hopefully left side equals the right side, and it verifies that this is a solution to this equation. This is a point on this line. So let's keep going. So we have 4 plus 5, so 9. So yeah, this would be a possible solution. Let's keep going. We've got some other ones to verify here. We have different values to plug in for x and y. Left side should equal right side. Yeah, that one checks out. And one last one, still the same. If I'm going quick, pause the video. So 2 times 3 this time, right? Remember, it's always x and y, plus 4. We have 6 plus 4, 10. Well, the right-hand side was 9, so that means that no, that's wrong. So these are solutions. These points are solutions. They are on the line, and we'll see how this is a line in the coming sections. 2x plus y equals 9. How's that for an abstract idea? Putting this on a graph. Okay, so like I say, this section, I'm getting ahead of myself, is only about the numbers. So what we're going to do is take the next equation and we're going to verify these possible solutions. So we switched up. We have a different linear equation here. It's linear, it has x's and y's and no exponents in it. And this one's saying, check these ones out. If x is 3 and y is 4, is that point on this line? Is that a solution to this equation? And so to do this, we're going to sub those values in and check. So 3 times 3 minus 4, 9 minus 4, yeah. So that one's good. We're going to work our way through. I'm just going to show all my work as we go. Oops, did I sub in wrong? Oh, look at that. I subbed the wrong value in there. Hang on. I don't know why I didn't sub in with brackets too. My goodness. Y is 3. There we go. I didn't sub in with brackets over here either. There we go. No, that one doesn't check out. 9 does not equal 5. Keep going. Subbing in carefully this time. For me, maybe you're being careful. Watch the signs, because the last one should check out. So we can't just come up with ordered pairs and check them this way. Same as what we were doing before, it's best if there's a mechanism, there's a way to solve these. Now, we have to have one number to then find the other. And so any value should give a corresponding other part of the ordered pair. So if I'm given an x, I can then solve for y. In this one, if I'm given a y, I could solve for x. So I'm kind of completing the ordered pair, if you will. So this bottom two are a little bit different. We have, again, another linear equation. And this time, we know what x is equal to, but we don't know what y is equal to. So what I'm going to do is sub in the 5, where I see the x, but the y is still unknown. So I'm going to go through this process of solving for y now. This is why we reviewed the solving with one variable, right? I'd get that y equals 0. So putting this back together as an ordered pair, we would have 5, 0 is a solution, right? It is a point on the line. You don't have to write all that. Really, all you really need to do is solve for y. But kind of rolling it all in together, I get a chance to say all this stuff. Okay, so the other one, same equation. This time we've picked a value for y, so now we have to solve for x. So we're going to take the equation and sub in the value we know as y, and now solve for x. X should equal 1. And again, really doing everything, that's more than the question even asks for, we know then that 1, 4, as an ordered pair, is a point on this line, right? It's a solution to this linear equation. We're going to play with these concepts in sort of all very similar questions, but they're sort of asked in different ways. And so this time we have a different linear equation. This time it says that we have x equaling 4, so what is y? Ultimately, that's the question we're trying to answer here. So what I'm going to do is take my equation and sub in the 4 where I see the x. The rest of it I'm going to copy, so now I can solve for y. So I'd have 8 plus 3y equaling 26. I'm going to subtract 8 from both sides. Remember, you add and subtract first, then do the dividing. I get 3y equaling, was that 18? Divide both sides by 3. So I get that y equals 6. Basically, we've got an ordered pair of 4, 6 as a solution. And again, this is sort of overkill because the question is just asking you, what is y if x is 4? Let's do another one here. So we've got the same equation. This time I know what y is equal to, so I copy out the equation, subbing what I know in, and prepping myself to solve for the other variable. Now, subbing 0 in is really awesome because anything times 0 is 0, and that basically all just goes away. So I'd have 2x equaling 26, way quicker to solve. I'd get that x equals 13. And again, the name of the game here, that answers the question, but kind of overkilling it, what I've got is 13 and 0 as an ordered pair is a full solution to this linear equation, or I could say it's a point on the line. So the next 4 give us a chance to complete the ordered pairs, and because I've been giving like really full answers to all of these, we've kind of already done this. So really just kind of hammering home again the same thing. In the ordered pair, this is telling me that x is equal to 9. And so I can sub 9 into this linear equation right here to solve for y. So I'd be subtracting 9 from both sides. I'd have negative 3y equaling negative 3. Divide by that coefficient. Watch your negatives in this one. I'd get that y equal to 1. And I could just complete this ordered pair with that answer. The next one is another ordered pair. And again, there's an infinite number of ordered pairs that would actually work as solutions. So this time I know that y is equal to negative 1. So I'm going to sub in a negative 1 where I see a y in that original equation. X equaling positive 3. Watch your signs. Subtract 3 on both sides. I get that x equals a 3. And I could complete that ordered pair with that answer. That is a solution to the equation. It is a point on that line. The last ones are subbing in zeros, which are really quick to do, or relatively quick to do. So I'm going to sub in a 0 where I see an x. So here's the first x subbed in as 0, 3y equaling 6. That goes away, it's essentially not there, and I'd have negative 3y equaling 6. So I can just divide by the coefficient straight off, nothing to move around, nothing to add and subtract, and get an answer of y equaling a negative 2. So completing this ordered pair, when x is 0, y is negative 2. That would be a point on the line. The last one here, this tells me that y this time is 0. So subbing in a 0 where I see the y in that original equation. Super quick because all that goes away, and I can just see that x equals 6. And so I can complete this ordered pair, completing the solution, another solution to that equation. We've done 4 different solutions to that one equation, and finding another point that would be on that line. Okay, one more. You can give these ones a try. I'm going to show all my work. If you want, you can just work while I talk or fast forward. Basically, what I'm saying here is if x is equal to 10, what is y equal to? So I'm going to take my equation, again it's a different equation this time, and I'm going to sub a 10 in where I see that x. Now I can solve for y. I would subtract 20 on both sides. That would get it away from my y. I'd have 5y equaling negative 20. Divide by 5, and I get y equaling a negative 4. So negative 4 would go up in my ordered pair here. Sorry, that's messy. Okay, another one. So this time it says, what is x if y is 4? So I'm going to copy out my equation, subbing a 4 in where I see that y. I'd have 2x plus 20 equaling 0. Subtract 20 on both sides. That would get it away from my x term. Oops, I haven't been drawing that there, sorry. And I'd get, sorry, I got lost. 2x equaling negative 20. Divide by 2 on both sides, and I get that x equals a negative 10. So I'd put a negative 10 in my ordered pair. It's a little messy there. Sorry, I'll get rid of that. Oops, I got rid of the negative too. Negative 10 there. The last one's subbing in the 0 for the x, remembering that this tells me it's x because it's the first spot in the ordered pair. Where I see the x, I put in a 0 in the equation. That's 0. Now I'd have 5y equaling 0. Divide by 5, divide by 5. This is not undefined, it is on. It's 0. Do that in your calculator if you need to, but y equals 0. So 0, 0 is a point on the coordinate plane. It is the origin. It's where the two number lines intersect. Last one, you might notice you don't really need to do this one. What this one's saying is, what is x when y is 0? Having a strategy when you don't see through to the answer is good, because you could have just seen through to the answer. We've already done this one, right? If x is 0, y is 0. Well, if y is 0, then x is going to be 0, right? We've just done this question sort of two different ways to find the same answer. So all we're doing with these is finding solutions, but you need to be given one of the pieces of information, right? Then it's just like solving a one variable equation. So some applications of these ones, these are all a little bit goofy. You can, for a short minute, imagine you run a stapling manufacturing company. And every time you make and ship a stapler, you're going to profit $1.80 on that stapler. But for you to keep the lights on and to employ, I don't know, maybe like you and your dog, I'm not sure what it is, what you can do for $120 a day, that's the cost. So there is an equation, and this is a little bit tricky to come up with on your own. I've said the two variables are going to be P for profit and X for the number of staplers. So we want to write an equation figuring out what the profit is when we make staplers. So the profit is going to equal $1.80 on each stapler. Remember, X is the number of staplers, but you'd have to cover your wage, keep the lights on, whatever it is. And so here I kind of for you have developed an equation. This would mathematically define how much you would make if you were to ship any number of staplers. So this question here says, okay, well, let's say this two variable equation, we want to know how much you're going to make if you ship 500 staplers. So what that is X equals 500, and it says what then would be your profit. So we can take this equation, and what we're going to do is sub in 500 where we see our X. I could then grab my calculator and do the math on this. 1.8 times 500 is 900. and then you're going to subtract the 120 from it. So your profit is equal to 780, or your profit would be $780. So two variable equations can work two different ways. So this one says maybe you have rent to pay or a credit card to pay off or something. You need to generate $1,500. How many staplers are you going to have to ship on that day in order to make $1,500? So X is a question mark, right? That's what we're looking for, is how many staplers. If our profit is $1,500. So let's take that equation, and what we're going to do is sub in what we know, this time 1,500 for the P, 1.8x minus 120. So in this one, it's a little bit trickier. We want to solve for x. We're going to use the skills that we have been with solving one variable equations to move things around and get x all by itself. So that would be 1,500 plus the 120, so 1,620, equaling 1.80x. I'd have to divide by 1.80, and you'll notice this one is a little bit funky. Hopefully that hasn't thrown you, but I left the x's on this side. Up to this point, we've always been putting x's on the left and numbers on the right, but it really doesn't matter. If you isolate it just to one side, that's fine. And in this case, it's a lot easier than having to move everything all over the place and getting a whole lot of zeros. So on my calculator, 1,600 divided by 1.8 gives me x equaling 900. And what that means is you'd have to ship 900 staplers to raise that $1,500. Okay, I don't think I'd go into stapler manufacturing. Doesn't seem like that easy to make very much money. This one is also sort of an oversimplification of real world stuff. So it's saying that there is a tumor in a patient that is very obedient and has been mathematically modeled to obey this equation. And so what this is saying is that W is the weight of the tumor, and D is the number of days of treatment. So I think it's always important to come up with a bit of a code, like what are W and D representing? So, we've moved off that XY coordinate plane into real applications. I think in all of our questions, you're always given the equation because coming up with them can be a little bit tricky. This one is also a little bit tricky. It says find the original weight of the tumor. The original weight of the tumor would be on day 0, right? It hasn't been treated yet. And if you were assigned this question, I think I'd put this tip in here for you. So what we're going to do is go back to that equation and sub a 0 in for the D. So that's copying out that equation and subbing in the 0 for the D. So now we need to solve this for the weight. Well, subbing in a 0 is really quick. The weight is 32. That means that it's a 32-gram tumor to start or before any days of treatment. All right, so this is a very obedient tumor. You're going to cure this cancer and figure out how many days of treatment until the tumor is totally gone. And so what we're saying with this, how many days would it be for the weight to be 0, right? That would mean that the tumor is gone. So we're going to take that original equation and sub a 0 in where we see the W. I'm not going to sub it in with brackets because it's going to look overly complicated. So negative 1.6D plus 32. The algebra is a little bit trickier on this one to solve. I'm going to start by subtracting 32 from both sides. Get negative 32 equaling negative 1.6d. And this one happened again where the d's happen to be now on the right-hand side. As long as they're only on one side, and we'd get just the d by dividing by negative 1.6, we have solved our equation. So I would use my calculator there. D is equal to 20, which means that 20 days, the tumor is gone. Whoops, done, gone. There we go. I don't know that tumors are that obedient. It is an example of a two-variable equation where if you know one number, you can always solve for the other, which is really the key to this section.